Section 2.3, modulus argument form of complex numbers. Now all this is another way to write a complex number, and this is where we use the modulus and the argument. So you'll remember that the modulus of a complex number basically was the size, wasn't it? And we used Pythagoras to find that, and I said that was the notation that we use. The argument was basically this angle that was in radians, and the way that we wrote that was argz. Now if we take those two values, it's actually possible to work back to find the original complex number in the form a plus bi, but what's even more useful is to look at how this can be written in terms of sine and cos. So let me show you what I mean. Have a look at this diagram that's over here, and let's see if we can work out the lengths of x and y. Yeah, so I've got the length of the hypotenuse, which is the modulus, and I've got this angle here, which is the argument. Is it possible to find x, and is it possible to find y? I think it is. Let's go back to some GCSE trigonometry. Cos and sine. Now this side at the bottom here, which is x, that's slightly adjacent, isn't it? So imagine if you had a question at GCSE, you had the hypotenuse, which we do have, which is called r, and you knew the angle here, and you wanted to find x, which is the adjacent. Well, you would use cosine. And what you would do is you would cover up the bit that you want to find in the cosine triangle, which is a. You'd cover that up and you say, well, I'll do the cos of the angle times by r. So let's do that. So this side x, we could say, is r cos theta. Yeah, so the hypotenuse times cos theta. Right, let's look at the side marked as y. So this one here. Now if this was GCSE and I had a hypotenuse in this angle, I want to find the opposite, you would use sine. And because we're trying to find the opposite, you'd cover that up with your hand or book or whatever it is, and you say, right, I'll do the sine of the angle times the hypotenuse. And in this case, the sine of the angle would be sine theta, and the hypotenuse is r. So this is r sine theta. So r cos theta is basically this size, and r sine theta is basically this size here, how long that is, which happens to be the real part. So this part over here is basically the size of the real number, and this part over here is the size of the imaginary number. So what that means is we can write a complex number in this form using the modulus and the argument. So the real part would be r cos theta, and the imaginary part would be r sine theta. Now if you factorize that, we get the modulus argument form of a complex number. So you take r out and you get cos theta plus I sine theta, and this is very useful. So it's another way of writing a complex number by using its argument r, and it's argument theta and its modulus r. So that's the modulus of the complex number, which we know how to work out. And this, they're both the same. This is the argument of the complex number. And there are reasons why we might want to write it in this form, because there's other types of calculations which we can do when the complex number is written in that form, and this form makes it easier. Okay, so express z equals negative root 3 plus I in that form. So we used the methods from before to find the modulus and argument, which means you must draw a diagram. So I've got negative root 3 here, and it goes up by I, which is 1. So that's that. And I know that the argument is going to be this. So however I work it out, I might need to add pi over 2 or take away my value from pi to find the argument. So let's start with r, that's the easy bit. So r is going to be the square root of 1 squared plus negative root 3 squared. So that's basically 1 plus 3, 4, square root of 4, 2. So r is 2. Now I'm going to do the argument a different way. I'm going to call this x. Yeah. So I could say that the argument of z, which is that thing theta that I want to find, is equal to pi, like 180 degrees, minus x. Okay, and now we're going to find out what x is. So if I draw that triangle for the angle x that I'm trying to find, this side is root 3. Now we don't use negatives because we're talking about a length. So you don't use negative root 3. Okay, negative just tells you which side. We just want the size. So x is going to equal the tan inverse of the opposite 1 over root 3. I think this one gives us a nice value. So in radians again, tan inverse 1 over root 3. And we get pi over 6, or 6 pi. So x equals pi over 6, which is a 6 pi. So the argument is pi minus a 6 pi, or pi over 6, which gives us 6 pi, or 5 pi over 6. So that's the argument, yeah? So we needed a diagram to help us with that, otherwise we could end up working at the wrong angle. So all we do now is to substitute our argument and our modulus into our modulus argument form. We just substitute into that now, easy. So it's just 2 cos 5 pi over 6 plus I sine 5 pi over 6. That's it, done. That's all we need to do, modulus and argument. Same type of question here, same method as example 6. Draw a diagram. Draw the complex number, so it's -1, -1 and negative I. So it means it goes that way. So this is the argument. So we can't work out directly. Maybe we need to add it to pi over 2 or take it away from pi. So what I'll do, I'll work out this angle here and I'll call that x to find the argument. So the easy bit is the modulus of the complex number r, and that's just the square root of 1 squared plus 1 squared, so it's just root 2, so we'll leave it like that. The argument of z, which is theta, that's going to equal, now I could say, another way of saying it is negative pi over 2, or negative pi, which is like all the way around. So all the way around to there is like negative pi plus x. Yeah, there are other ways of doing it, but this time I'll do negative pi basically plus x to work out what the angle is. You could just work out what the angle is and then put a negative sign in front of it. So let's draw a little triangle. You don't need to draw this. You could probably quite easily do in your head, or work out what the sides are. So both of these sides are 1. Now, we probably don't even need a calculator. If both of those sides are 1, it means it's an isosceles triangle. Now if it's an isosceles triangle, the two base angles are the same. That means both the angles are the same. That means x is 45 degrees. But since we're working in radians, that's pi over 4. So I didn't even need a calculator. You might recognise that fact. If you did do the tan inverse of 1 over 1, you would get pi over 4, or a quarter pi, you get the same thing. So my argument is negative pi plus pi over 4, which is a bit like doing negative 1 plus a quarter. So it'll be negative 3 pi over 4. So final answer is root 2 outside the bracket, and in the bracket cos, and then in brackets negative 3 pi over 4. Because it's a negative number, we want to put it in brackets plus I sine negative 3 pi over 4. Done. Right, you should now be able to do exercise 2E on page 24 of the textbook. Now moving on to the second section, we can use this modulus argument form to easily multiply and divide two complex numbers. Okay, now all this stuff is from the book. I'm going to show you in a really easy way what basically we're doing. So in modulus argument form, let's say we want to multiply two complex numbers in modulus argument form. What we do, the two complex numbers, we multiply the moduli. So you take the modulus of each number and you multiply them together, okay? And then we add the arguments. So we add the two arguments of the two complex numbers. Let me just do an example. So let's say I've got one complex number, Z1, and that's R1 cos theta 1 plus I sine theta 1. And then I've got another complex number, Z2, and that's R2, so it's got its own moduli and a different argument of cos theta 2 plus I sine theta 2. So two complex numbers. Let's say I want to multiply them. That means I'm doing Z1 times by Z2. So if I multiply the moduli, I just do R1 times R2 to get the modulus of the answer. If I'm going to add the arguments, I do theta 1 plus theta 2, and I get the argument of the answer. Yeah, so multiply the r's, add the arguments. Right, and now if we're going to divide two complex numbers, so we want to do z1 divided by z2, so that may be written like this instead. Well, you probably already worked it out. We divide the moduli. Moduli is just pure for modulus, so we don't say modulus is. We do R1 divided by R2, and the arguments, well, we just subtract the arguments, so we subtract arguments, and that's going to be theta 1 minus theta 2. It's that easy. Yeah, so basically this is what all that stuff at the top is saying. You either multiply and add, let's put it here, so you either multiply and add, or you divide and subtract. Multiply the moduli, add the arguments, or you divide the moduli and subtract the arguments, and what you will get is the answer without actually physically multiplying and dividing the complex numbers in like a plus ib form or bi form. Right, so we've got a complex number z1 and that other one I'm guessing is Z2, because Z1 can't be two different complex numbers. So first thing we want to find out is what's the modulus of the first one times the second. So if we were to multiply them first, yeah, what would be the modulus of the new complex number? Well, that's equal to the modulus of the first one times the modulus of the second one. Yeah. So the modulus of the first one is 3, modulus of the second one is 4, so it's just 12. So the moduli basically of the answer, that's what this bit means here. Okay, moduli after you multiply. Well, the moduli after you multiply is the original moduli multiplied. Okay, second part of part A, the argument of Z1 times Z2. Well, that's just the argument of Z1 plus the argument of Z2. Remember, we just add the arguments together, so I said 2. And that's just going to be where the argument of the first one is 5 over 12. And then we're going to add pi over 12. So that will give you 6 pi over 12, which simplifies to pi over 2. Then in part B, we want to write what the product of those two complex numbers is in modulus argument form. Well, that's easy because we've got r and theta. So 12, r1 times r2, and then cos, and the new argument is pi over 2. So that just goes in the brackets. Easy, easy, easy. And then the part 2, we want to write it as a complex number, x plus iy. All we do is expand the brackets. So to get a, all I do is 12 times whatever the cos of pi over 2 is. Yeah, so I'm basically just doing this, that times that, then that times that. So 12 times, and my calculator still needs to be in radians, times the cos of pi over 2. That gives me 0. Black, 0. And then, oh sorry, they've used x and y, haven't they? So let's call that x. Since they've used x. And then y is going to be 12 times sine of pi over 2. So 12 times sine pi over 2. That's going to be 12. So basically the complex number is just 0 plus 12i, or just 12i. Yeah, so expanding the brackets, working out what the actual answer is for that calculation, tells you what it is in a plus bi form. Right, so we now got these two complex numbers, but there's a problem. Look at this, look at that. There's a minus sign there. Okay, first thing, in modulus argument form, the sign in the middle must be positive. Yeah, it must be a plus sign. If it's not, we're going to have to use a couple of tricks to change it to a plus sign. Now, there's a couple of identities which you're going to learn in year 13. Now, an identity is basically two things in maths which are identical. And the two identities you're going to learn in year 13 pure are these, which I need to show you now. The first one is this: the cos of an angle theta is equal to the cos of the negative angle. Okay, e.g. this could be an angle. Cos 72 equals cos negative 72. Try it on your calculator so you get the same answer. And then the other one is sine or negative sine of an angle equals sine of the negative angle. Example, negative sine 50, I'm just picking random angles, equals sine negative 50, and that will work for any angle. And we're going to use these to help us change that minus sign to a plus sign. So let's start with Z2. It's got to be written in the right format. So Z2 equals cos 2 pi over 5 minus I sine 2 pi over 5. Right, so we're going to use that second rule with cos. There's a 3 there, so let's put a 3 in front. We're going to use the second rule to change this bit here. Yeah, because it's negative sine something, we can change it to plus sine and change the angle to a negative. Can you see basically what happens with sine is that negative sign can go there. It moves from in front to the angle, and we can do that because they're equivalent, they're the same. So let's do 3 cos 2 pi over 5 plus I sine. Now we write negative 2 pi over 5. We're allowed to do that. But there's another problem. The angles inside the brackets must be the same. One's a negative and one's a positive. So let's write that down here. The angles must be the same. We can't have a positive one and a negative one. It doesn't work. So what we need to do is to change that this angle here so it matches that one, and we can use this identity to do it because a negative angle and a positive angle, they're equal. So I can change that to a negative angle. So what I now get is negative, or 3 cos negative 2 pi over 5 plus I sine negative 2 pi over 5. There we go. It's now in the right format. Now we can multiply them and work out Z1 times Z2. So Z1 times by Z2, what do? We multiply the arguments. So it's going to be 2 times 3, which is 6. Multiply the moduli. We add the arguments. Now, when I add them, it's basically going to be pi over 15 plus negative 2 pi over 5, like this, plus I sine pi over 15 plus, so we're adding a negative argument, negative 2 pi over 5. So let's work that out and see what we get for that. Right, so the argument becomes negative a third pi. So negative pi over 3 in both, plus I sine negative pi over 3. Right, and now all we need to do, if we want to write it in form x plus iy, we expand the brackets. So x will equal 6 times cos negative pi over 3. Y will equal 6 times sine negative pi over 3. So let's work out what we get. In radians, 6 times cos negative pi over 3, and I get exactly 3. And in the y part, 6 times sine negative pi over 3 is negative 3 root 3. Negative 3 root 3. So that will give us our final answer of 3 minus, I'll put the I here to avoid any confusion. I don't want people thinking it's underneath the square root sign, so I could put the I there, or I could put the I here in the middle. Yeah, so I would avoid putting the I here just in case. unless you leave loads of space and you know that it's definitely not under the square root. Right, here's a division. So division means that we need to divide the moduli and subtract the arguments. Now you can see the signs here are positive, and the argument, they're both the same, both got the same signs, so that's fine. So we don't need to use the identities that we did in the last ones. We can just go ahead and do the working. So the argument of this new complex number is going to be root 2 divided by 2. So I suppose I could leave it like that. Now I think it simplifies. Is it 1 over root 2? I think. Let me just check. Root 2 over 2. What's that become? Oh, it just stays as root 2 over 2. Something like that. And the argument of this new complex number is going to be pi over 12 minus 5 pi over 6. So when I do these, I don't bother putting pi in. I just type in 1 over 12 and I subtract 5 over 6. And then I know there's going to be a pi there. So I get negative 3/4, which is negative 3/4 pi. Oops, that's meant to be a pi there. Negative 3 pi over 4. Okay, so in modulus argument form, I've got root 2 over 2 times by cos negative 3 pi over 4 plus I sine negative 3 pi over 4. So all I need to do now is expand the brackets and work out what the real and the imaginary part is. So what do we get? So x is going to equal root 2 over 2 times by cos negative 3 pi over 4. Y part, the imaginary part, is going to be root 2 over 2 times by sine negative 3 pi over 4. So let's work out what we get. So root 2 over 2 times by cos negative 3 pi over 4, and I get negative 1/2. Now to save time, what I'm going to do is scroll back and just delete the cos and change it to sine. I think I can do it. Can I do that? Oh, unfortunately I can't. I've got to type the whole thing in again. You can't just delete cos. Right, so times by sine, and then same thing again, negative 3 pi over 4. It'd be so nice to be able to press a button for pi rather than doing shift all the time. Make things easier. And that's negative 1/2 as well. Half. So my complex number is going to be negative 1/2 minus 1/2 I. Right, you should now be able to do exercise 2D on pages 27 to 28 of the textbook.